Hi, welcome to your first online session of Physics 2101. My name is Yahya Al-Saleh. Some of you might know me, the others might not. I usually teach section 30, but for the rest of this semester, I will be teaching all of the sections. Now I'm going to try and fix this screen sharing. And hopefully it is working well now. Okay, it should. As you can see, this is my first time teaching online, just as it is your first time learning online. And that means it is challenging for both of us. So we are going to try and learn from each other as we go on. And I welcome all feedback. You can email me, and I actually welcome you to email me after this lecture to tell me what I can do better. Okay, in terms of office hours, they will be announced soon, inshallah. Your first point of contact will still be the lecturer that you are used to see. So whether it be myself, Dr. Noor Al-Huda, or Dr. Rao. And yeah, we'll try to take it from here on. So after this lecture is uploaded, I'm actually going to be uploading another lecture that is a very, very quick overview and revision of everything we have done up until before this lecture. Okay, so make sure you take a look at that. So we have reached to the point where we're discussing potential energy and conservation of energy. And that is, well, what is potential energy? As we have said, it is the energy of an object as a result of its position. So it's not actually doing anything, you're not doing anything to it. The mere fact that it is at a certain position, whether it be because of gravity, so it's not at zero level, or because of something like a rubber band, so this is your natural position. If you start stretching, it will end up having some stored energy. And conservation of energy. So let's move on. How do we read a potential energy curve? Now, we have learned in the previous lectures that potential energy or work in general is the integral of some function over its position. Okay, so we started with f dot d, w equals f dot d, and we said that's equal to fd cosine theta. And from there on, we ended up saying, okay, but what if it's a continuously changing force? We ended up with an integral. Okay. Now, what is the opposite of integration? Say we already know the potential of something, or the potential on something, and we want to know, okay, what force is it going to experience due to that? Well, the opposite of integration is differentiation. And as we all know, differentiation is a much, much nicer mathematical being to play with rather than with integration. It's usually much easier to differentiate something rather than to integrate it. So let's take a look. Now, I'll be looking to this side because my screen is on this side and the camera is on this side. Bear with me. Now, let's look at a potential energy curve. If we differentiate whatever we have, okay, we will get minus the slope against the x curve. Now, it's important to remember this will only work for a conservative force. Just like we said, those equations in the first place only work for a conservative force. If it's non-conservative, it's a totally different ball game. We don't really care about it much at this point. Okay, let's look at one-dimensional motion. We have f of x equals minus du by dx. Okay, let's take an example. We have the elastic potential energy. Okay, due to an elastic band or due to a spring, for example. our potential energy is U equals half kx squared. Okay, say we know something has some sort of energy. Now what do we do with it? Well, if we say the potential energy is half kx squared, then the mere differentiation of it will give us what? Let's do it together. Well, we go from f of x equals minus du of x by dx, and we just plug it in. So we do minus d by dx of half kx squared, and that would simply be minus 2 kx over 2, which is simply minus kx because the 2's cancel out. Yeah? Okay. Let's take another example. Okay, say gravity. What is U for gravity? We know U for gravity is mgh. Okay, let's plug it in again. F of x due to gravity will be equal to minus du by dx, which is minus, it's too thin, I'll go back to the bit thicker one, which is minus d by dx of mgx, because h is simply the distance, and we get minus mg. And we know for something that is falling in free fall, F equals mg, and depending whether we say g is positive upwards or downwards, you can say it is minus mg. Okay, so far so good. Let's go back to our screen. Okay. Oops. Okay. So let's do an example. Okay, now usually we would do a PIQ and you would vote over it, but we can't do that now. So I'll simply explain it, how it goes. Let's take a look. The graph you see in front of you gives us the potential energy for a system. Okay, it's only one dimensional, so we don't have to worry about 2D and 3D. And we have region AB, BC, CD. Where on this do we have the biggest force whatsoever? Well, we know we're only concerned about magnitude here, so absolute terms. We know the force is the differential of the potential. We also know that the differential of a curve is simply its slope. So by looking at this, we can say that CD has the biggest slope, so that's where it will have the biggest force. AB has the second biggest slope, so that's the second highest force. And well, BC has a slope of 0, so if you take the differential, it will be 0. So that is the least amount of force, which is 0. We cannot have negative force, at least not in terms of when we're talking about magnitude. What if we write the mechanical energy? Mechanical energy is the total energy of a system if it has potential and kinetic energy. So we add the two up, we have our total mechanical energy. Now let's take a look at how the kinetic portion of this energy, of this mechanical energy, varies with the potential. I'm pretty sure all of us know how it goes like, because we did take a look at this in the previous lectures. There were some nice simulations we did with pendulums and with pendulums and with springs. Okay. Well, if we just simply rearrange, our kinetic energy is whatever remains from the mechanical energy once we take out the potential. Why is that useful? Let's take an example. Let's look at turning points. You're driving your car, and at some point, you have a rather steep curve in the road. Okay? Those of you who go on, to Amrat often will know what I'm talking about. I have to move my video because it's actually a bother at the moment. Okay. Now, at equilibrium points, this is very, very important. Kinetic energy is equal to 0 because your velocity is equal to 0. But your force is not equal to 0. And you know your force is not equal to 0 because if you have ever been in a car where someone suddenly starts going on a steep turn, you will all end up being attached to one side of the car or the other. Okay, so there is a force that is actually taking place. Why? Well, let's take a look. This is a plot of the potential energy versus your position. Okay, so you start with a lot of potential energy, and then suddenly that goes very low, and then you go a bit higher and a bit lower again, and then you go up again, and then it's stable again. What do these points tell us? What these points tell us, and I just got an idea to make this a little bit easier for us. I'm going to be doing this. So, okay, so this should be hopefully better. This is a plot of the potential energy, which means we can get the force directly out of it by simply looking at the slope, or mathematically by differentiating. Okay, what happens here? Take a look. If we take the differential at every single point and draw a graph of the slopes, okay, well, A, we know it's minus du by dx, so we will get minus whatever plot we have here. Okay, so if the plot, how do I use a pointer? Here. So if here we have positive, here we will have negative, negative, positive, and so on and so forth. Let's see how do they match. At this point, you have 0 slope, so you have 0 force. At this point, you have a very good slope, so you have a very strong force in the positive direction. Here you have 0 slope again, only for a little bit, but then again, that is 0 force. Here you have a slope, so you have a strong force. Well, mild force compared to the first one. Again, 0 slope, 0 force, and you are starting to see the idea of what is happening. And then eventually, when you have an entirely flat slope, you get an entirely flat force. So you don't experience any forces anymore. Let's take an example in numbers. Let's say our total mechanical energy is 5 joules. This is the black line. Then we have a plot of the potential energy. And this is very interesting because at one point our potential energy seems to be more than our total mechanical energy. We'll come back to that. Our kinetic energy is, as we said, the mechanical energy minus the potential energy, which is this difference. So here, it's simply 1 joule. Here it is 5 minus 1, so that would be 4 joules. And again, 2 joules, and again. And here it's 0, and now we have a problem. Our kinetic energy is minus 1 joule. Now that's not possible, and we know that's not possible because kinetic energy is half mv squared. If there's a square there, the square of something is always positive unless it's an imaginary number. So that either means our velocity is imaginary, so we're not really going anywhere, or that v squared is negative. Doesn't really work out. So this isn't useful. This point here, where we have the two lines intersect, is called a turning point. My kinetic energy here is 0 because 5 minus 5 is 0, but my force is not 0 because look, we have a slope. Yeah. So we still have the problem of the minus 1 joule. What do we do with that? Let's try something different. Let's say my mechanical energy is instead 4 joules now. So at this point, it will be 0. Okay. At the right side, we don't have a problem. At the left side, we still have a minus 2 joule now problem. We'll get back to that. But those points where we have 0 kinetic energy, but my force is not equal to 0, okay, are very, very important. On the left-hand side, we have a kinetic energy of 0 and a force that's not equal to 0. On the right-hand side, we have kinetic energy of 0, but also force equals to 0. Now, what's the difference? The differences between those two are exactly like those in the photos. In one of them, this is a very, very stable equilibrium point. And the other one with the elephant, a slight movement will take us to a very, very big problem. Let's take a look now at this middle point, an unstable equilibrium. What is that? Let's actually go back. Okay. These 2 points, okay, are neutral equilibriums. They're nice equilibriums, okay? So this ball down here is not going to move. It's not going to go anywhere. If we go to the right, it will still be stable. It's not gonna suddenly gain any sort of kinetic energy, okay? The left-hand side, which we said it was a problem because we had minus 1 joule and minus 2 joules, is what we call a forbidden zone, okay? We cannot go to the forbidden zone because we cannot have negative velocities, okay? Which makes this equilibrium point, although the force there is not equal to 0, it still makes it a neutral equilibrium, a safe one. On the other hand, okay, this bit in the middle, okay, is problematic because if I go slightly to the right, I will fall down all the way here. And if I go slightly to the left, I'm gonna fall down all the way to x2. This is like having a small ball on a semicircle. It's stable, but barely, okay? It's like getting a pencil standing on its edge. Let's go very, very low. What's a stable equilibrium? A stable equilibrium is the best kind of equilibrium. Look here. If you are here at this point, okay, no matter what you do, you go to the left, you go to the right, you're still going to come back to exactly this position. Think of a big marble before a small hole. Now, if it manages to go through that hole, it will gain energy because it's going to lose potential energy and gain kinetic energy. But the problem is, it really cannot go through that point now, can it? That hole is too small. So that's a stable equilibrium, one where no matter where you go, you still end up where you started unless you put in a really, really large amount of energy. Look at this pendulum in the corner down here, okay? We can think of it as this area between those two black circles. When it's at the upper left, it's here, maximum potential, minimum kinetic. When it's at the right, it's right here. And when it's at the center, it's here. It has its maximum kinetic energy and absolutely zero potential energy. But no matter where it goes, it keeps trying to go back to the center. Let's try another checkpoint. We have the potential energy function for a system where the particle is in one-dimensional motion again. Now the particle is in the region AB. What is the force on it? Well, if we do minus du by dx, now the du by dx is the slope, and the slope here is negative. But since we have a minus before the equation, our total force here will be positive, because minus times minus is a plus.